Hello everybody, this is Philip Jonas at Kalamazoo Valley Community College presenting OpenStax Principles of Economics. And today we're covering module 12.1 through 12.6, Negative Externalities. In this module, you will learn how to explain and give examples of negative externalities, contrast the equilibrium and socially optimal price and quantity, explain command and control, pollution charges, and marketable permits, and evaluate the efficiency of command and control and market-oriented regulation. So our module today is all about negative externalities. And if you are unfamiliar with that term, what we're looking at is a situation where the cost of bringing a product to market isn't just borne by the firm that supplies the product. So the cost that the firm itself incurs, we refer to that as the private cost. And if there are no negative externalities, what is really neat about market outcomes is that it balances these private costs with the benefit of the product to the buyer through a voluntary market transaction. But the presence of a negative externality means that in addition to the cost that the firm itself bears, there is an external cost to this product, which is being borne by people outside of this transaction. So in order to distinguish between what a product costs the firm itself to provide versus the total systemic cost from a social point, we introduce the term social cost, which represents the combination of the private cost of production plus that external cost. So a classic example here, of course, is pollution if firms don't have to pay for it. So as a simple graphical example, let's start out with a market for refrigerators. Until now, we've discussed this in terms of course, a demand curve, which represents for all the refrigerators that could be being bought here, how much each buyer is willing to pay for it. And then a supply curve representing the cost of production to the firm, which again, we're going to highlight here as a private cost. Now, the market outcome in the absence of a negative externality can be referred to as efficient. There's a couple of different ways you can think about that. So, perspective number one, if you want to focus on sort of traditional welfare analysis, consumer and producer surplus, is that the value of these refrigerators is represented by the numbers on the demand curve, the cost of production by the numbers on the supply curve. And then what's great about the market outcome right here is that we're producing every refrigerator whose value exceeds the cost of production. So consumer and producer surplus are maximized. Or, second perspective, a little bit more advanced from our more recent modules, is that in an efficient market, the price of the product falls to the marginal cost of production. A private supply curve, of course, represents the marginal cost of production, and we see right here at equilibrium, our refrigerators are selling for $650 each, and indeed that final refrigerator that's being sold, refrigerator number 45,000, has also a marginal cost of $650. So, yay, efficiency. But now let us introduce the notion of a negative externality. Let's say that producing and later discarding refrigerators has some type of negative environmental impact. And of course, there's sort of many dimensions to what these environmental impacts are, but for the sake of simplicity, let's summarize it into a dollar figure, and let's say we estimate that to be about $100. So that's a cost that this product imposes on society, which goes above the private cost that the firm incurs. So the $100, we refer to that as the external cost. And then we can draw into our supply and demand diagram a second supply curve. I know it sounds a little weird the first time you hear that, right? Two supply curves at once. We call this a social supply curve or a social cost curve. So here we're now having a look at the supply of refrigerators in our economy, but using social cost as the benchmark, sort of the total integrated systemic cost of providing a refrigerator. And of course, what we see right away is the outcome that the market produces, that equilibrium outcome, E sub 0 here, is actually not that great anymore. You can take both perspectives again. You can look at refrigerator number 45,000. You can say, hey, what's the social cost of producing this refrigerator? Well, we got to look on the social cost curve, and it's like $750. But the person who's buying it, look at the demand curve, it's only worth $650 to the person buying it. So here the market is providing a product at a social cost of $750 that only provides $650 worth of consumer benefit. So that product literally makes us poorer from a social standpoint. Or perspective number two, if you want to talk about price versus marginal cost, the price of the refrigerators determined by the market is $650, but the marginal cost of that final refrigerator actually much higher, $750. So again, mismatch between price and marginal cost. We're looking at an inefficient outcome. So that means just letting the market handle the situation is not quite good enough anymore. We'll want to come in here with some type of government intervention. Now, today we're going to have a look at what these government interventions can look like, but let's start out by showing the goal of the government intervention. It's not like we want to ban fridges altogether. After all, there are still plenty of fridges that have a buyer value even above the social cost of producing them, but we do have to tweak this market outcome a little bit, look at the intersection of the demand curve and the social cost curve to get the socially optimal outcome. So let's distinguish that one more time. E sub 0 here, that's the market outcome, the equilibrium, what the market does if we just let the thing do its own thing. And we want to distinguish that from the socially optimal outcome. I'll designate that E sub 1, which is the desirable outcome that maximizes the wealthiness of our society. So look what we're looking for in terms of our socially optimal outcome. Number one is, of course, we want to see fewer fridges made, 40,000 instead of 45,000. Again, not total ban, we just want to pull back a little bit, because up to fridge 40,000, the buyer value of these fridges actually exceeds even the social cost of production. So those make our society better off. Or alternate perspective, if you like the price versus marginal cost perspective, at this outcome E sub 1, the socially optimal outcome, the price of a fridge would be $700, which at that point is equal to the social marginal cost of producing that final fridge. So again, E sub 1, efficient, E sub 0, not. But the rub is, market by itself produces E sub 0. Now, part of course, defining our objective here comes down to being able to quantify that external cost. You know, how much higher is the social cost of whatever's happening here than just the private cost incurred to the firms? And that can take so many different forms, right? Like, are we talking about a pollution situation? What type of pollution is it? Is it that, you know, a nearby river is getting polluted and now maybe it's number one, bad for the animals, but number two, people can also not use that river for recreation? Is it a global phenomenon where we're putting a pollutant into the air that makes the entire planet worse for us? Is it noise pollution, right? So just sort of something that's annoying to the neighborhood, but certainly lowers the value of living there. So many flavors of these external costs. And if you have an interest in this, you can take an upper level econ course in environmental economics that goes all into how we can estimate these sorts of external costs. I do want to mention one example to you though, simply because it's sort of fascinating from an economic standpoint, and also the underlying mechanic is easy to understand but widely misunderstood, so it's great for us to talk about a little bit. One type of external cost that we sometimes have to contend with is that the actions in the market can produce an actual risk to human life. So the regulation we're eyeing here is in terms of we are reducing the risk across a group of people. Now, in order to put a number on this benefit, we use the concept of the value of a statistical life, which is a widely misunderstood concept. So many people see that and they're like, oh, you're putting a price on whether an individual lives or dies. Well, that's basically impossible, at least within the tools of economics. Maybe some other disciplines figured this one out, right? Instead, what we're actually doing is we are summarizing a small risk across a big population, and we are summarizing it in terms of one fatality across the population so that it's easier to think about. And there are a couple of different ways you can estimate what the value of a statistical life is. For example, you can look at what people are voluntarily willing to pay for safety. For example, additional safety devices on a car. You can survey people on, how much additional risk they are willing to take in order to save how much money. Although surveys are typically not that great in the social sciences. And then finally, something that I think is just so fascinating is the idea of a compensating risk differential. We can look at the labor market and see how much people get paid there to take on more risky jobs. So there's a variety of these jobs you can look at where they exist in sort of a less risky and more risky version, right? And if it's a more risky version, there might even be a great reality TV show attached to it, like let's say an ice road trucker versus a regular trucker, that sort of thing. But I'm going to go with a classic example, made up numbers, but they aren't completely crazy and too far removed from reality, in order to show you the simple math that underlies such a value of a statistical life. So one compensating risk differential we could look at are window cleaners. So window cleaners, of course, have a certain amount of risk associated with them by default. It's a physical, labor-intensive job, but a somewhat riskier version of it is a high-rise window cleaner, because obviously if you're high up and then something goes wrong, and that ends a few lives every year. So what we can look at is the market for window cleaners then, and how much the salaries differ between the regular risk and the higher risk version. And just for an example here, let's pick some nice and clean numbers. Let's say an ordinary window cleaner makes $30,000 per year, while a high-rise window cleaner makes $40,000 a year. So to the extent that we consider the skill sets equal, and they aren't 100% equal, but for our math example here, let's say it's exactly the same job, we would say the additional compensation of $10,000 per year is a compensating risk differential. It's paying you for the chance that you might die on the job. So then we can look at the actual additional chance of dying on the job. And again, for the sake of argument, let's pick a really nice and round number here. Let's say that a high-rise window cleaner has a 0.1% additional chance of dying per year over an ordinary window cleaner. So in other words, 1 in 1,000 additional window cleaners die per year if they choose the high-rise job. So the idea of a value of a statistical life then becomes a very simple math formula. We take the pay differential and divide it by the risk differential. So we look at our two jobs. Pay differential is $10,000. We look at our additional mortality risk, 0.1%. Let's express that as a decimal so that we don't end up making an embarrassing mistake about, how the division works. And we find $10,000 divided by 0.001 is, of course, $10 million. This would be one way of putting a price on what sort of regulation is worth it from a safety standpoint. If we can adopt regulations that save additional lives at a price less than $10 million, it's worth it from a cost-benefit standpoint, while regulation in excess of $10 million would not be worth it in terms of what people themselves are willing to take on in risk versus benefit. Now, this $10 million number, it isn't the actual number for the United States, because it turns out when we do safety regulation, different departments use slightly different numbers. Let's say the Environmental Protection Agency versus the Department of Transportation, but it is in the ballpark of what we currently use for values of statistical lives in the United States. So what this means is, let's take this back to the idea of regulating pollution, because that's a little bit easier to talk about, is that our initial graph we were looking at in terms of the market was showing the underlying product being produced, refrigerators. And then if refrigerators have an additional external cost that places the social cost above the private cost, the idea is the market outcome is not efficient. We instead want that socially efficient outcome, which sees somewhat fewer refrigerators at somewhat higher prices. However, we can also flip this entire perspective on its head, such as with the value of a statistical life, and this is more often how we really talk about regulations in real life, and talk about the regulation in terms of the benefit it provides at the margin versus the cost it provides at the margin. So for example, one type of marginal benefit would be, what if we save lives? And then we could say, well, the marginal benefit per statistical life saved, again, not individual lives, $10 million. And then we look at some sort of cost function. Well, what sort of safety measures can we adopt? Ideally, we would want to adopt every safety measure where, for example, like QA here, benefits greater than cost. We would not want to adopt safety measures where cost exceeds benefit, QC here. And of course, the ideal level of regulation would be the one that balances cost and benefit at the margin, QB. But we're done talking about the value of statistical lives. We're back to pollution. And what you have to sort of pay attention to when you're looking at a marginal cost and benefit graph like this is, earlier we were looking at the supply and demand of refrigerators. We were looking at the underlying good being produced. You increase on the x-axis, there are more refrigerators. Now we're flipping our perspectives and we're talking about pollution being reduced. Technical term for that is pollution abatement. So basically 0 point on the x-axis here means we're not reducing any pollution. Everybody's just polluting as much as they want to. And then as we advance on the x-axis, we are cutting pollution. So more cuts, of course, mean less underlying pollution. It's the opposite perspective. One more time, the idea is we want to adopt a regulation where we cut every unit of pollution, where the benefit of cutting it exceeds the cost, until we hit that ideal level where at the margin, cost and benefits are balanced. This is the framework we will adopt for the rest of this module in order to now look at our standard methods for pollution abatement, but with a little bit of creativity, I think you can also see how they could be applied to other negative externalities that are not necessarily as sort of straightforward as an amount of pollutant put into the air. The general category here that we are operating in is referred to as market failure. So what that means is if we leave the market to its own devices, we don't get the socially efficient outcome. And anytime we encounter such a market failure situation in economics, broadly speaking, you can put the solutions that we have available into 3 major categories. First one is referred to as command and control regulation. Command and control means there are laws or other regulations that say specifically, here's what you have to do, here's a command. So for example, you can only emit so much pollution, or you must install this pollution reduction technology. So for example, a catalytic converter on a car, that would be an example of a command and control regulation. Everybody must have these catalytic converters on their cars. And then control, of course, if you don't follow the rules, there is some type of punishment. And we're talking about this in the realm of pollution right now. Obviously, you could, for example, also apply that to safety regulation. Let's say you've got a high-rise window washer. You could pass a law that says all high-rise window washers must wear a helmet, for example. And then over on the market-based side of our regulation, we've got 2 major techniques. The first one is referred to as pollution charges or pollution taxes. And it's a very different perspective on the problem. Here we're saying you can emit the pollution you want, but every bit of pollution you do, there is a penalty tax associated with it, sort of an excise tax. And finally, perhaps the type of regulation that most people are least familiar with, and it's also the newest type of regulation to get applied, very clever in its own right, we'll look at it last, marketable permits. So at first they look a little bit like command and control. They place a limit on how much each firm can pollute, but this limit is being issued in the form of a permit. So rather than saying you can only emit so much, we give you permits that say you are allowed to pollute this much, and you can only pollute what you have permits for. And then the really interesting bit, so here the marketable part, once the permits are issued, firms can actually buy and sell those to each other, which just has a fascinating outcome. But let me take you through these three in order, because I think that'll make it most obvious what the trade-offs are. So let's start with our command and control regulation. We want to abate some amount of pollution. And of course, the underlying problem is it's not free, otherwise we'd already be doing it. The more pollution we want to abate, the more it costs, not just in total, but the marginal cost also increases. Because of course, if you want to reduce pollution, there are some methods you can adopt that are cheap. And then once you've got the cheap ones out of the way, by definition, the next ones you do get more and more expensive per unit of pollution you want to reduce. So there's some type of pollution here we want to get in line. Let's say, it's an air pollution problem. We've got maybe an acid rain problem or something along those lines. So we've got some environmental engineers that had a look at this, and they said, okay, what we have to do is we have to reduce the amount of particles we put into the air by 30 pounds. Here's our limit. So ideally, of course, what we would want to do is we would want to do all the cuts that are cheap to do in order to get to the 30 units we have to cut out, while not engaging in the cuts that would be more expensive. That's sort of the job of economics here. We have a goal. How do we do it efficiently? That's where economics comes in. So what's the problem here? Well, the underlying problem is that different firms, different places have different cost for cutting pollution. So for our example, we'll just say there are two firms here. That's it. And each of those firms currently emits 30 units of pollution. And now we're placing an abatement schedule here on the slide. Abatement schedule means abatement is how much you cut, right? If you don't cut anything, obviously there's no cost associated with that. But looking at firm A here, for example, cutting 5 units of pollution has a marginal cost, so cost per unit, of $100. So if you want to cut 1 pound of particulate emissions, that's $100. You want to cut 3 pounds, that's $300. 5 pounds, $500. But the more you cut, the more expensive it gets. The first 5, they come in at $100 each. The next 5, okay, now you've got the easy stuff out of the way, cost goes up. Now it's $150 for each of those, and so on and so forth. You can see by definition, the more you want to cut, the more the cost goes up. However, while the cost goes up within the firm, across firms, there's no reason for these numbers to be equal. And so many reasons for them to be different. For example, firm A and firm B, they might be producing different things. So there's no reason to suspect that cutting pollution is equally expensive. Or maybe they produce the same thing, but they use different production processes. Or maybe one firm has an older plant and it wasn't designed with upgrades in mind. So doing this pollution reduction is just going to be more expensive because it's a more custom solution, and so on and so forth. So let's say we've got firm B, and firm B can also cut pollution, but it's more expensive for firm B. So you see here, first 5 units, $150, next 5 units, $250, and so on and so forth. This is the fundamental problem of regulation. Cutting pollution doesn't have the same cost everywhere. And what we want to do is we want to cut pollution where it's cheapest. Now you could look at these two tables and you could say, okay, I can pick out the 30 units that would be the cheapest. And you can. But the problem is, if you are the regulator, you don't necessarily know these numbers because you're not running these firms. And if you go to the firms and say, hey, show me your numbers for cutting pollution, well, let's just say there's going to be some pretty big numbers getting reported to you because everybody knows how this works. The lower of a cost of doing something you report, the more likely you have to do it, the more likely you'll be stuck with those costs. And if there's some sort of reimbursement, the less reimbursement you will get. So like there's just this inflating of cost estimates going on. You can see that anytime there's an environmental regulation that's proposed, whether it's, a sensible one or a not sensible one, doesn't matter. Firms will report very large estimates for what it costs to comply. So how do we deal with this? Well, sort of the most obvious solution, which is also the most old school solution, very brute force, is what we call command and control. Hey, we know that there's different costs to cutting pollution at different places. We don't know what the underlying numbers are, so let's just play it safe. We'll do a blanket rule across the board. Everybody has to cut the same amount of pollution, and if nothing else, we'll at least achieve our goal, which is of course the most important thing. We want to achieve the goal at a cost that's average. So it's not a terrible approach, but we've got better stuff we'll show you in just a second. Let's take this as an opportunity, though, to learn how we would evaluate the efficiency of this approach. So we've got a blanket rule that we want to make, and the goal is cut pollution by a total of 30 units. So if we only have 2 firms, blanket rule, of course, is going to be, we're going to ask each firm to cut back by 15 pounds of particulate. Let's go back to our firms. So that means each firm has to incur the cost of the first 5, the next 5, and the next 5, because we want to cut a total of 15 units of pollution. And for each 5 block, we now have to add up. Firm A pays 5 times 100, 5 times 150, 5 times 200. Firm B, 5 times 150, 5 times 250, 5 times 350. So let's look at the implementation cost of this particular regulation. Here's firm A, 5 times 100, 5 times 150, 5 times 250. Firm A has to spend $2,250 to upgrade its plant in order to reduce particulate emissions by 15 pounds. Firm B, with the always higher cost, 5 times 150, 250, 350, has to pay $37.50 to upgrade its plant. And then as an economist, I look at the situation and I say, okay, the social cost of complying with this regulation is it would cost us $6,000 to get particulates reduced by 30 pounds. And that's the social cost. Now, who has to bear that cost? Do the firms have to pay for these upgrades because, they're the ones doing the bad thing? Is the government going to reimburse them? Is there going to be some cost sharing? Well, that's a little bit more of a political decision. The point of the matter is it's going to cost our society $6,000 worth of resources to get the job done. So taking that back to the idea of marginal benefit and marginal cost, we would now look at the benefit of reducing particulate emissions and ask ourselves, is it worth it to spend $6,000 to cut 30 pounds of particulates out of the air? That's the marginal cost versus marginal benefit approach. Great. But before we make that decision, let me introduce you to newer solutions that let us achieve the same amount of abatement at a lower cost. And that, of course, is going to have 2 benefits for us. Number 1, lower cost is just good by itself. If we decide to do this thing, we're saving money, all of us are richer. Fantastic. But also, this presents a real environmental benefit. Because if we look at the marginal benefit of cutting the pollution, and we can achieve this at a lower cost, we can cut more pollution for the same amount of money. Some units of pollution that wouldn't be worth cutting if a command and control approach is all we've got under our belt are now worth cutting using these more modern approaches. So sort of everybody's a winner if we can up efficiency, which is of course the job of economics. So here's our next approach to abating pollution. Instead of saying, let's reduce by 30 units, instead of focusing on the quantity, we are instead going to introduce a pollution charge or tax, where we put a tax cost on each unit of pollution, thereby creating an incentive for firms to cut. Now, what exactly is that tax cost in order to cut 30 units of pollution? Well, if the regulator doesn't know the underlying cost of cutting pollution, we might not get the number right immediately, and we might have to play with this tax a little bit till we achieve our goal. But for the sake of simplicity here, let's pick a number out the gate that gets us the same reduction, 30 units, so that we can compare the efficiency to what we were doing before. So I'm going to introduce a pollution charge now, which means, for our example here, I'm going to say $275. That's how much you have to pay in taxes for every unit you don't cut, for the units you still pollute. So we go back to our companies, and of course the companies are going to do whatever is cheaper. So here we look at firm A, for example. It's emitting 30 units of pollution. If it does nothing, it would have to pay 30 times $275. But it can save itself some money, because it can look at its first 5 units and say, well, I would have to pay $275 for each of those 5 units of pollution if I do emit them. But if I cut them, well, that only costs me $100 per unit. So instead of paying 5 times $275, I can pay 5 times $100. And I'm coming out ahead. So I look at my next 5 units. Pay $275 for each of these, or pay $150 to reduce them, right? You see, it's actually a very simple decision. For each block of units, you're just asking yourself, do I cut 5 units? Or do I pay 5 times this tax? Every time cutting the units is cheaper than $275, you cut the units. So you cut the next 5, and firm A, because it's got the cheaper cutting cost, is now actually going to increase how much it cuts compared to command and control. It will cut 20 units. And then the last 10 units would cost more to cut than paying the tax. For the last 10, it will pay the tax. Firm B has the higher cost of cutting, so it's going to make a slightly different decision. Look at the first 5, less than $275. Okay, we're going to cut those. Next 5, less than $275, cut those. Next 5, $350. Nope, better to just pay the tax. So compared to command and control, firm number B is going to cut less and pay the tax on 20 pounds of the particulate. But as I promised, we're immediately starting out here with a tax number that gets the job done. Let's see how much pollution is getting cut. 5, 10, 15, 20, 25, 30 units are still getting cut. Crucially, what changes is who does how much of the cutting. Firm A, which has the cheaper cost of cutting, cuts more. Firm B cuts back. So if we look at the social cost of cutting pollution this time, firm A pays 5 times 100 plus 150 plus 200 plus 250. Firm A pays 3,500. They cut more than before. Firm B only 5 times 150 and 5 times 250 spends $2,000 cutting, cuts less than before, which means we add these two numbers up. The cost of cutting the pollution is not 6,000 like it was under command and control. We could make it cheaper. We could get that cost down to 5,500. Same amount of pollution cutting, cheaper cost. This is economics in action. We're achieving our goal more efficiently, which again all makes us richer, but also makes more environmental protection worth it. Win-win scenario. Now, of course, from the perspective of the firms, it might not be so much of a win-win scenario, because remember, they also have to pay taxes, right? So let's go back to the firms for a second. Yes, firm A is cutting 4 blocks, but it's also paying 10 times 275 in pollution tax. Firm B paying 20 times 275 in pollution tax. So that's 30 units of pollution tax being paid, 82.50 going to the government. The firms will certainly be unhappy about that. But from an economic standpoint, That's not a social cost because the money is now in the hands of the government, which could spend it on other things. Or if you want to be like sort of extra nice about it, you could say, okay, if the government is collecting these taxes, maybe it can cut other taxes on the firms and thereby actually make the firms better off as well. Again, it's a little bit more of a political question. The point is we can get it done for cheaper. These are pollution charges or pollution taxes. And then finally, we get to the most up-to-date way of abating pollution, which doesn't necessarily mean it's always the best one, because frankly, it's a little bit more complicated than the pollution charge. But it's a very neat solution for a particular class of problems. So you definitely want to be aware of it. And this one's referred to as marketable permits. So let's go back to the marginal cost of cutting particulate emissions here. Let's say our environmental engineers have determined, hey, we have to cut 30 units of pollution. We're still adopting the same goal. What marketable permits allow us to do is to put that limit in place directly, just like command and control regulation, even if we don't know the underlying marginal cost. But we can do it in a way that makes it just as cheap and efficient as pollution charges. Sort of a nice combination there. So we get both benefits of the command and control and the pollution charges, but there's a downside to it. It is the most complicated system, both in terms of understanding it and also administering it as a regulatory system is a little bit complicated. Doesn't mean we don't do it. Like, for example, the United States actually got acid rain under control using this sort of system, using tradable sulfur dioxide permits. They get traded in Chicago, Illinois, using a pattern similar to what I'm about to show you. So how do marketable permits work? Well, step number one is a little bit like command and control. We make some type of blanket rule. Here's how much pollution has to be cut. Except in terms of phrasing it as a cut, we phrase it as an allowance. We say you cannot pollute except those pollution units you have permits for. And then, crucially, this is where the magic comes in, after we put this blanket rule in place, we will now let firms trade these permits, and that has a really cool effect. So let's go through the two stages here. So we go back to firm A and firm B, and we start out with a blanket rule, just like command and control. Only instead of telling each firm you have to cut 15 units of pollution, we sort of put that statement on its head and we say, hey, I see you're currently emitting 30 units of pollution. I'm only going to give you permits for 15 of them. So whatever you don't have a permit for, you have to cut, which of course, again, still as a starter position means each firm would have to cut 15 units of pollution. So looking at this as a little chart here, you can imagine as the green check marks the 3 blocks of 5 units that you've got pollution permits for. Now, I'm putting them at the bottom of the firm's charts because, of course, which units of pollution do you use your permits for? The ones that would be most expensive to cut. And the ones where you don't have permits, the first 15, those are the ones you choose to cut because they would be cheapest to cut. So this initial allocation looks literally identical to command and control. If this was the end of the story, firm A would now cut the first 3 blocks at 5 times 100 plus 5 times 150 plus 5 times 200. And again, over here, 5 times 150, 250, 350. We could add up this cutting cost. It would be $6,000. It would be just like command and control. But now comes the magic. After we hand out the permits, we tell these two firms, and hey, if you want to make a deal with each other where you buy and sell some of these to each other, go for it. We're totally okay with that because all we really care about is how much pollution gets cut total. We don't have a position on who does the cutting. It doesn't matter. We're just trying to protect the environment here. So put yourself into the shoes of each company here. So we're going to do firm A first. They've got a block of 5 permits here. Right now, owning that block of 5 permits means they do not have to cut these 5 units of pollution, which would cost the firm $250 per unit to cut. So those permits have real economic value to firm A. They are not just going to give them away for free. But what if firm A could get more than $250 for each of those permits? Sell for more than $250, cut for $250 because now you don't have the permits anymore, pocket the difference. You're making a profit. Let's look at firm B, the high cost cutter. Firm B has 15 permits and it's thinking about buying another 5 block, right? Like what if I could put a check mark here? I wouldn't have to cut the last 5 units of pollution, and those units cost me $350 to cut each. So I'm actually willing to spend money on some permits, because if I can get permits at less than $350, buying the permits would be cheaper than reducing that pollution. So firm A here, they make money if they sell permits for more than $250. Firm B over here, they make money if they buy permits for less than $350. There's a deal to be made here, right? Somewhere in between $250 and $350 is a per permit price where firm A is willing to sell 5 permits and makes money, and firm B is willing to buy 5 permits and also make money. Now, I can't tell you exactly where in the range of $250 to $350 this deal will be made. But I do want to pick a particular number because it illustrates a particular phenomenon. The price at which the permits are traded, if it's the same price as a pollution charge or tax, you end up with the same outcome in terms of what company does what. So for the sake of argument, let's just pick the same number as the tax. Let's say it's $275. So firm A is going to sell these 5 permits to firm B for a price of $275. Watch the mark move over. We're going to take it here from firm A. We're going to put it over to firm B. Here's the trade. So now firm A, it only has 10 permits left. It has to cut 20 units of pollution. So 5 times 100 plus 150 plus 200 plus 250, which you will recognize is the same pollution cutting as under the pollution charge. Likewise, firm B, 20 permits in possession. So they now only have to cut 10 units, 5 times 150 plus 5 times 250. Again, exact same outcome as under the pollution charge. So we add all of this together, and what we end up with are the exact same numbers in terms of social cost of cutting the pollution as under the pollution charge. Firm A cuts 20 units at a cost of $3,500. Firm B cuts 10 units at a cost of $2,000. Once again, we get that lower implementation cost of $5,500. So in other words, our 2 market-based approaches, pollution charges and marketable permits, they both can achieve pollution abatement at lower cost. The question is really sort of, what do you want to specify when you make your regulation? Do you have a dollar number in mind of up to what cost point pollution should be cut? Then a pollution charge makes sense. Do you maybe not know what the right dollar figure is, but you know how many units you want to see appear in total or cut that's mirror image of each other? Then you can do the marketable permits instead. Either, you set the cost or you set the quantity. The other one is going to be equivalent. And then sort of a slightly more subtle difference. With the pollution charge, of course, a side effect is the government's now also collecting a bunch of taxes of our two firms that, the firms have to pay in addition to cutting pollution. And maybe that's something that's desirable, hey, because you need some tax revenue anyway, so might as well do it in an environmentally friendly way. Or maybe that's undesirable because it'll throw up a whole bunch of political barriers. While with our marketable permit system, keep in mind these firms aren't just spending this much cutting pollution. We also have a trade going on. Firm B paid 5 times $275 to firm A. This is not a social cost, this is just a transfer. But it means that if you subtract this from the cost of compliance, what firm A is doing, the $3,500, and you add this to the cost of compliance of firm B, the $2,000, both firms are better off than under command and control. So you might be able to get a little bit more political support behind this, but there will be no tax revenue for the government from this particular system. And of course, finally, with the pollution permits, it's the most complicated system. So now the government has to issue permits and it has to operate this market where firms can trade with each other. A pollution charge is sort of cleaner, easier to implement. But it's great to have another tool in our toolkit. So that's it. We've talked about them today in terms of our negative externalities. But in general, when we want to fix a market failure problem of the pollution type or some sort of, incremental undesirable behavior like that, our toolkit always has the same 3 tools in it. You can do command and control, which, while it's typically less efficient, some problems you have to do command and control style. Like, for example, not that we normally think of it as an economic problem, think about the idea of people complying with stoplights. That's just going to be command and control. Like, you have to stop at the red light, and if you don't, we're going to penalize you. We're not going to implement a system where we let you trade permits to run red lights, right? Like, that's not right. But in instances where there is some allowable amount of a negative thing, such as pollution, and we don't particularly care who engages in the negative things, then the permits allow the negative behavior to flow to its highest value use. And the pollution charge, again, sort of flip side of a marketable permit, if instead we have a certain cost where we're like, hey, well, if it's providing a benefit that exceeds the cost of this pollution, then we're still okay with the pollution, so we'll just put an extra tax charge on engaging in the pollution. That's it. That's the 3 methods we have. So sometimes the way we express this in economics is in terms of what's called a production possibilities frontier. Basically, let's say we have 2 outcomes where there is a trade-off. Like, for example, we could talk about the outcome economic output, going back to the example of the beginning of this module. Let's say the refrigerators. Fridges are good. Fridges make people happy. But we have a conflicting goal, cutting pollution. Cutting pollution is good. Cutting pollution makes people happy. Then basically, the way we look at this in economics is the most efficient set of outcomes, here represented by the letters P, Q, R, S, T, are the ones that give us the highest combination possible of these goals. And which of these combos is the right one, P, Q, R, S, T? Economics might be able to help a little bit with figuring out how much do people value fridges versus pollution abatement. But really, a lot of that's going to be a decision outside of economics. Where economics has just so much value is by designing approaches that put us on that frontier to begin with. So I used the command and control with the particulate emissions as an example here. My command and control example that costs $6,000 to implement would be a point such as M here. That's inside of the efficient frontier. So what that means is by designing a better approach, such as a pollution charge or a marketable permit system, I can cut the same amount of pollution at a lower cost. So I get more economic output. I can go from M to Q. Or by keeping the cost the same for $6,000, I can now cut more pollution going from point M to S, or I can go from point M to R, give us more output and more pollution abatement than under the command and control approach. So that's where economics is great, to get us to the efficient frontier to begin with and give us the best possible set of trade-offs that are within our toolkit. And that concludes our discussion of Module 12.1 through 12.6, Negative Externalities. Hopefully in this module you learn to explain and give examples of negative externalities, contrast the equilibrium and socially optimal price and quantity, explain command and control, pollution charges and marketable permits, and evaluate the efficiency of command and control and market-oriented regulation. I will see you next time.